The next subject we are going to discuss is graph searching, or this is sometimes also referred to as graph traversal. And we are going to discuss two algorithms for this. One of them is the breadth first search, and the other will be depth first search. Okay, so breadth first search, it works by starting from a selected root vertex, which you can select randomly or according to a certain rule, exploring all neighbors of the root, your selected vertex, and then recursively repeating for each neighbor until a condition is met. So this condition could be visiting all vertices, or it could be, as the name suggests, a search, like if you encounter a value, a key value associated with the vertices, if you find it, you stop the procedure. That could be another application here. Let me show you an example here. By the way, these algorithms, depending on the order you select from the neighbors, for instance, may yield different results. So the outputs may not be unique for each application if you include randomness or if you include a certain rule. So if E is selected as root, then its neighbors B, C, G, and H, we call them visited. So you visit E, and then you visit its neighbors B, C, G, and H. Visit here might be processing that vertex, whatever to do. You might edit the graph. You might change or modify the key value embedded at those vertices, or you simply visit that vertex so you obtain its properties. So you select E as the root, then E is visited, and then you visit its neighbors, B, C, G, and H. Again, here, the visiting order, it could be random, or it could be dependent on a certain condition. For instance, if you use lexicographical order, in this case, in this certain example, the next vertex you will visit is B, and then C, and then G, and then H. Okay, but in a different application, doesn't have to be like that. You might visit G first, and then C first, and then B first, and then H. Could be a scenario. So depending on how you select the next neighbor to visit, the result of this process might yield different results. So next, let's say you visit B, C, G, and H. Now, in the actual implementation of these algorithms, you usually use a stack. If you don't know what a stack is as a data structure, you might look it up. But essentially, it's a first in, last out data structure. So here you have a certain order, B, C, G, and H. Assuming that I'm following the lexicographical order, I'm going to visit the neighbors of each of these, the neighbors that are not visited yet, obviously, in this order recursively. So I'm going to visit the vertices that are adjacent to B, and then to C, and then to G, and then to H, and then I'm going to repeat it in a recursive way. Now, the neighbors to B are D, E, and A, but E was visited earlier, so I'm not going to visit it. I'm just going to visit A and D. Since I'm using lexicographical order, the order will be A and D here. And then I'm not going to go further with A and D. I'm going to look at C next, because that's the next one in my list. And I'm going to look at its neighbors that are not visited yet. So A and E will be visited at that time. Therefore, the only one I need to visit is F. So I'm going to add F here. And then I'm going to visit the neighbors of G. And the only neighbor I can visit is I. So I'm going to visit it, and actually I will be done, even if I haven't checked the neighbors of H. But you see, the neighbors of H will all be visited by them. Therefore, the procedure is complete. Now here, my condition was visiting all nodes. Obviously, if your condition is different, like searching a key value, you can terminate this earlier if it is encountered. Okay, but in a general sense, we will discuss examples where we try to visit every vertex. Now, obviously, another parameter here is the selection of the root vertex. Here in this example, we selected E, but if you change it, the order of visiting will be different. For instance, if you select A as your root, the neighbors are B and C. So you are going to visit them next. And then you are going to recursively visit their neighbors, the neighbors of B and then the neighbors of C. Neighbors of B are A, D, and E, but A was visited earlier, so I'm not going to visit it again. So D and E will be visited. And then, since this is recursive, I'm going to visit the neighbors of C. The neighbors of C are A, E, and F, but A and E are visited at this point, so I'm just going to visit F. So up to this point, I have processed. Next, I will visit the neighbors of D, E, and F in this order, since I'm using lexicographical order here, in a recursive manner. However, as I said, you can use a random selection or some other criteria. It's not very crucial at this point for the implementation. So the neighbors of D are B, E, and G, but B and E are visited, so it will be G next. And then the neighbors of E, B, C, G, and H, but the only one that is not visited yet is H, so it's going to be next. And finally, the neighbors of E, yeah, I have visited them. Then the next one I need to visit is F, but all the neighbors of F are visited, and then G, so it will be I in the final step. Okay, so using lexicographical order for the neighbor ordering and selecting A as the root, this is the order that breadth first yields. Obviously, if you have other, for instance, if you select other vertices as a root, or if you apply other criterion for selecting the next neighbor to visit, you can have different sequences here.